The title of my talk is Multiphoton and Side Channel Attacks in Mistrustful Quantum Cryptography. This is work in collaboration with Mathieu, Bozzio, Adrien, Cavaille, Eleni, Diamanti, and Adrian Kent. My research is funded by the UK Quantum Communications Hub. I would like to thank the organizers and committees for organizing Qcrypt 2022 and for the opportunity to present my work here. Mistrustful quantum cryptography is a large field and one of the major applications envisaged for a global quantum internet. It includes important tasks like bit commitment, coin flipping, oblivious transfer, and secure computations. In this paper, we have identified new multiphoton attacks on practical implementations of mistrustful quantum cryptography with photonic setups and have shown that some previous implementations were vulnerable. We illustrate the power of these attacks with an experiment and also discuss side channel attacks. The results discussed in this paper are based mainly on the following task, which is a primitive to construct more complex cryptographic tasks. We call this task private measurement of an unknown qubit state. Alice sends Bob a random BB84 state. Then Bob generates a random beta privately and measures the received state in one of the two BB84 bases, the computational basis if beta is 0 or the Hadamard basis if beta is 1. Bob sends a bit message M to Alice reporting whether a measurement outcome was produced, the case M equal 1, or not, the case M equals 0. Here in this figure we illustrate a particular photonic setup to implement this task. We see that Alice encodes the BB84 state in photonic degrees of freedom using an approximate single photon source and a polarization state modulator. Bob chooses his measurement basis with a wave plate which can be set in one of two positions, and also using a polarizing beam splitter and two threshold single photon detectors. Security against Alice is the property according to which the probability that Alice guesses Bob's bit beta is arbitrarily close to 1/2. Here we assume that Bob is honest, therefore we are going to discuss only the case in which Alice tries to cheat. Security against Alice can be achieved in ideal settings where step 3, the communication of the message M by Bob, is not needed. However, in practice, losses, imperfect detectors, and other experimental imperfections require step 3, compromising the security of the task. Moreover, in practice, multiple detectors click with non-zero probability. Therefore, Bob must carefully choose how to report the successful measurements to Alice. This defines Bob's reporting strategy. I'm going to discuss various reporting strategies by Bob, focusing on this setup that we call setup 1. Multiphoton attacks comprise strategies by the dishonest Alice in which she sends a pulse to Bob. This pulse can have an arbitrary number of photons encoding an arbitrary quantum state which can be arbitrarily entangled. In particular, Alice can have a quantum system, an ancilla, which can be arbitrarily entangled to the photons sent to Bob. And Alice tries to guess Bob's bit beta from the message M received from Bob. That is, in general, what multiphoton attacks are. In the following, I will describe some particular reporting strategies and the multiphoton attacks arising in these strategies. So first, we have a simple reporting strategy in which Bob reports as valid measurements only those in which one detector click. This would seem as a natural strategy, but it opens up the possibility for Alice to implement the following attack that we call multiphoton attack 1. Alice sends Bob a photon pulse with a large number of photons in the same BBT4 state, as discussed in this paper. Ideally, if Bob measures in Alice's bases, and if we have the ideal setting in which Alice's and Bob's bases are perfectly aligned and there are no errors, then all photons sent by Alice will arrive to the same detector, and therefore only one detector will click. Otherwise, in the case where Bob chooses a basis different to Alice's basis, a large number of photons will go to each detector, and therefore both detectors will click. So we see that in this way Alice learns beta from the message M. Because if Bob measures in Alice's bases, only one detector will click and Bob will send the message M equal 1. If Bob measures in a different basis, both detectors will click and Bob will send the message M equals 0. So this is we have here discussed the case of an ideal setting. In practice, there will be errors and misalignments in the bases, but still this attack applies because Alice can guess Bob's bit beta with high probability. We have implemented an experimental simulation of multiphoton attack 1. This was performed by our colleagues Mathieu Bozzio, Adrien Cavaille, and Eleni Diamanti in the University of Paris. We see here the results showing that by increasing the average photon number of Alice's dishonest pulse, Alice's guessing probability of Bob's bit beta increases very close to unity. So this is an attack that is a problem in practice, and therefore we should implement countermeasures. A simple countermeasure is changing the reporting strategy. Instead of using just strategy 1, let us consider now what we call reporting strategy 2, in which Bob sets a measurement, a valid measurement, if at least one detector clicks. That is, in this setup, if one or both detectors click. In this case, we have shown in lemma 1 in our paper that if the detector efficiencies are exactly equal, then this protects Bob perfectly from arbitrary multiphoton attacks. Of course, guaranteeing exactly equal efficiencies is impossible in practice, but attenuators can help. So in the case in which Bob uses reporting strategy 2, or more broadly, if he sends the message m equal 1 with unit or high probability if both detectors click, we call multiphoton attack 2 to any strategy implemented by Alice that allows her to exploit the difference in Bob's detection efficiencies. Another particular reporting strategy is symmetrization of losses. This was introduced in this paper, and roughly the idea of this strategy is that Bob discards detection events from the most efficient detectors or bases, aiming to equalize his reporting probabilities. This can offer very good protection to Bob if Alice's pulse has 0 or 1 photon, and if Bob's dark-count probabilities are small, as we have shown in lemma 2 in our paper. But because we want to prove security against dishonest Alice, we have to assume that she might be dishonest. So we have to assume that she is not necessarily sending a pulse with 0 or 1 photon. She can be sending pulses with various photons as more convenient to her. It follows that Bob is not guaranteed the perfect protection claimed in this paper from the symmetrization of losses reporting strategy by Bob. This is a crucial point because various important experimental demonstrations of mistrustful quantum cryptography use symmetrization of losses and claim security based on the suggestion of this paper that this can provide security. But given this observation, this claim of security does not follow. Now I discuss probabilistic reporting strategies in which Bob sets the message m equal 1, meaning Bob reports a measurement as valid with a probability that depends on which detectors click and on Bob's measurement basis. We know that the previous strategies are special cases of probabilistic reporting strategies. Another strategy is the trivial reporting strategy, in which Bob assigns as valid measurements all detection events with the same probability, for example, with unit probability. That is, in this case, Bob accepts all detection events as valid, including those in which no detector clicks, in which 1, 2, any number of detectors click. This is the only known reporting strategy offering perfect protection against arbitrary multiphoton attacks. But it requires extremely good setups with very low losses and high detection efficiencies to be useful in practice. For example, to guarantee that the protocols work correctly. In this table, I summarize multiphoton attacks 1 and 2. Multiphoton attack 1 applies when Bob reports double clicks as valid measurements with 0 or a small probability. As discussed, a proposed countermeasure is then reporting double clicks with unit or high probability, or using the trivial reporting strategy if consistent with experimental parameters. So in the case in which Bob reports double clicks with unit or high probability, we are now in this situation, and then multiphoton attack 2 applies when Bob's detection efficiencies are different or not close enough. A proposed countermeasure in this scenario is then making Bob's detection efficiencies exactly equal or sufficiently close. Alternatively, using the trivial reporting strategy if consistent with experimental parameters. Our main result is Theorem 1 in our paper, which roughly says that if Bob's detection efficiencies are different, as we expect in practice, then the only probabilistic reporting strategy guaranteeing him perfect protection against arbitrary multiphoton attacks is the trivial reporting strategy, that is, the strategy in which Bob reports all measurements, all detection events as valid measurements. Or, in other words, in which Bob does not report any losses to Alice. A crucial point that follows is that symmetrization of losses introduced in this paper does not guarantee the claimed protection. And as I mentioned, this implies that various previous experimental demonstrations of mistrustful quantum cryptography, which have used symmetrization of losses, cannot guarantee their claimed protection. I summarize in this table how multiphoton attacks apply to previous implementations of mistrustful quantum cryptography. We have here 5 important experimental demonstrations of mistrustful quantum cryptography demonstrating different tasks like quantum bit commitment, coin flipping, oblivious transfer, in 2 different setups. Setup 1, which is the one we have discussed in this presentation, where Bob has 2 single photon detectors, and setup 2, which is a small variation of setup 1, in which Bob has 4 single photon detectors, and the basis is chosen passively with a 50-50 beam splitter, followed by wave plates, polarizing beam splitters, and the 4 single photon detectors. This paper, reference to, reports multiple clicks as valid measurements and therefore is covered against attack 1. Papers 4, 5, and 6 do not say whether they report multiple clicks as valid measurements, and therefore we don't know whether they were covered against attack 1. And paper 3, which introduced symmetrization of losses, explicitly says that they do not report multiple clicks as valid measurements, and therefore they were not covered against attack 1. We notice that none of these papers are covered against attack 2. So I will conclude with the following. In multiphoton attacks, dishonest Alice sends multiphoton pulses and obtains information about Bob's measurement bases. The trivial reporting strategy, where Bob does not report any losses to Alice, is the only known perfect protection, but it requires state-of-the-art experimental setups to be useful in practice. Some countermeasures are using attenuators to make detection efficiencies very close, using different setups to probabilistically infer if a pulse is multiphoton, aborting with double clicks, using variations of the task considered, etc. But all these open other problems, as we discuss in our paper. We have also extensively analyzed a setup with 4 detectors in our paper, including extensions of multiphoton attacks 1 and 2. Finally, in side-channel attacks, Alice controls 40 degrees of freedom, in addition to the degrees of freedom previously agreed with Bob that she would use to encode the quantum states. There is not currently any perfect protection against arbitrary side-channel attacks. Measurement device and fully device-independent protocols have other security and implementation problems, for example loopholes, as we discussed in our paper. Importantly, a countermeasure introduced in this paper by Lo and Chow that can provide unconditional security in principle against arbitrary side-channel attacks comprises Bob filtering Alice's signal via teleportation. However, a practical problem is that there is a non-zero probability of producing more than one pair of entangled photons. Thus, we believe that this requires further investigation. With this, I conclude, and I would like to thank you for your attention.